morning. We are going to continue with our studies on scaling dimensions and issues. We had an introduction about scaling, the scaling laws, and whatever is involved in the initial part of our lecture. We concentrated on material properties. Now, there are three things which need to be looked into. One would be the material properties that we have already covered. The second would be the processes, how the processes at microscale are going to be different, are going to be affected when we reduce the scales, when we reduce the size of the device from centimeter to millimeter to micron and beyond. So, we are going to look at different processes and how do they get affected due to the reduction of the device to micrometer lengths. And finally, we will see a few devices and the peculiarities of their operation in terms of different scaling and how the equations, the governing equations which are valid, for example, Navier-Stokes equation in fluid flow, how the Navier-Stokes equation can be modified or should be modified, and which are the terms which would be important when the system size is reduced. So, just an example, like when we think of Navier-Stokes equation, there is a body force term, and that body force term will not get affected no matter whatever be the system size, but the viscous and the convective terms will change, or the magnitude of them will change as we reduce the system size. So, one has to look at the contribution of the different terms and their related processes in the overall scheme of things. That means, certain process may become important at microscale which we need not have considered in the macroscale process. So, we will identify certain phenomena which will be more prominent in microscale systems in today's class. So, first we think about the root cause of any transport, be it momentum, heat or species. Now, when we have a difference between the temperature, pressure or concentration at two different points, it's the gradient which is going to cause molecular transport of heat, mass or momentum between these 2 points, between these two surfaces. So, these gradients are the driving forces for any kind of transport, and if we could increase the gradient, then the overall then the transport phenomena of that specific type will get enhanced. So, the capital X in here denotes the property, the property which can be measured. It could be pressure, it could be temperature, or it could be the concentration of this species. So, this gradient of dx over a certain distance x would tell us the magnitude of this transport process. So, if we can increase the gradient, the corresponding transfer flux will increase, and as a result of which the equilibrium state will be achieved faster compared to the previous case when the gradient was smaller. Now, the direct implication of this is that we need to consider the surface effects which can be dominant in microscale, and not only the mean transport processes will increase due to higher gradients, less predominant processes and coupled processes may gain importance. And additionally, the transport coefficients that we know of, the value of diffusivity or thermal conductivity may change when the system size is reduced. So, these are the effects which one needs to be considered. So, in the next slide, we are going to see the effect of these coupled processes, the processes which could be neglected in a macroscale process and how they become more prominent at microscale process. And when we talk about the coefficients, we know that the coefficients we assume them to be a constant over a certain operational range if the temperature etc. remain constant, but for high force gradients the linear relations which are applicable for macroscopic systems, for example, Newton's law or Fourier's law, needs to be expanded in order to in higher order terms are to be incorporated, which signifies the relaxation time for first processes. So, any high energy density process such as laser processing or first chemical reactions, for example, which may happen in explosions, you need to add additional terms, you need to provide additional terms in the flux relation so as to explain the process. Now, we know that for a temperature difference of 100 Kelvin per millimeter, the linear relationship is valid. Now, 100 Kelvin temperature change over 1 millimeter is quite large. We do not come across such high temperature gradients in macro processes, but when we convert this into microsystems, this refers to about 0.1 Kelvin per micron. Now, there are certain processes in which at the microscale these kind of temperature gradients are commonplace. You will find such temperature gradients taking place in micro devices. So, whenever that happens, the linear relationship for the transport coefficients, in this case the thermal conductivity, which we generally consider for macro systems, will need to be expanded by including higher order terms. So, the processes not only have changes like the unimportant processes become important, but the relations will also change when you go from macro to micro scale. And the dependence of thermal conductivity, for example, on the crystal structure is also has also become important. For example, if we think about conduction in a crystalline substance, then it may so happen that at small scale the thermal conductivities at different directions, different planes of the crystals are different. So, anisotropic conduction, anisotropic heat conduction in crystals need to be incorporated into Fourier's law so as to find out the total amount of conductive heat transfer in such small systems. So, the thermal conductivities at different crystal planes. So, a tensor equation has to be written incorporating the thermal conductivities of the crystal at all possible planes, and that has to be used in the thermal heat conduction equation. Now, we also have to think about the characteristic lengths. Now, that we know that transport processes benefit from shorter distances, and we can have rapid cooling or heating since the process is faster, and we get this much, it's about this much of temperature gradient for sensitive products. So, we have rapid mixing, that is something which we need to take into account. Rapid heat transfer giving rise to gradients where the linear relationship of the transport properties or transport relations need to be expanded, and we get a situation in which the concentration gradient that one can obtain would be very high, like because like the temperature gradient here is high, the concentration gradient could also be very high, and this would lead to rapid transport such that this is going to give rise to quick homogenization. So, if you are dissolving a substance in a micro device, then the high concentration gradients, since the concentration changes over a very short distance, this would give rise to a quick dissolution of the substance, and the concentration gradient, high concentration gradient ensures that the system comes to equilibrium at a faster rate compared to a macro system. Now, the selectivity of fast parallel chemical reactions, as we have seen before, it can be increased with rapid mixing, and this is one of the major advantages. This can be tuned to become one advantage of microreactors. Now, length scaling often correlates with time scaling of the relevant processes. In generally speaking, the shorter the length and the shorter will be the characteristic time. So, if we think about dissolution of a substance or one component getting diffused into another component, or two liquids flowing side by side, and due to diffusion there is going to be some sort of overlapping or some sort of mixing taking place at the boundary of these two immiscible solids, then the time scale of mixing for a micro device, due to the shorter length of transport, the time scale is going to be faster, a lot faster than the macroscopic systems. So, this is definitely one of the biggest advantages of micro devices, where the transport length is small, the transport time is small, the overall system reaches equilibrium at a time much before than that takes place in a macro device. So, by tuning these processes, one can suppress undesirable reactions in a specific reaction, undesirable side reaction, and can promote the reaction that one would like to have. So, the microstructure devices are well suited for rapid processes, but they are also quite sensitive to any change in the process conditions. So, this has to be kept in mind as well. So, but at the same time we may have several characteristic times of mixing, of residence time in the device, and one has to adjust the other processes to yield an optimum result. Now, this figure is this table is quite interesting to look at. Now, when we were discussing about macro processes, we all know that velocity gradients is the root cause of momentum transfer, and the relation which connects momentum transport with the velocity gradient, that is the fluxes and the driving forces, would be Newton's law. When we know that if there is a temperature gradient existing in the system, energy transport is going to take place, which is a vector quantity. So, Fourier's law provides the relationship between the driving force, temperature gradient, and the energy. On the other hand, when we talk about mass, the reason for mass transfer is concentration gradient, or some sort of a pressure, some sort of a gradient which is created, and this is governed by Fick's law. So, these three laws and these three processes we are familiar with, that is Newton's law, Fourier's law, and Fick's law tell us the magnitude of momentum transport, energy, and mass transport. But there are two other effects which needs to be taken into account, which are shown here as Dufour effect and Soret effect. Now, it has been found, it has been seen that if we create a temperature gradient in between 2 points on in a medium, then that will give rise to mass transport between point 1 and point 2. So, mass transfer not only takes place as a result of concentration gradient, it can also take place as a result of temperature gradient, and this effect is known as the Soret effect, and the diffusion coefficient corresponding to temperature induced mass transport is denoted by the Soret coefficient dAT, which is a function of temperature. Similarly, if we have a concentration gradient in between two places, then that may also give rise to energy gradient, and this is known as the Dufour effect. Normally, the temperature gradients or the concentration gradients necessary to have this kind of heat transfer, this kind of mass transfer and heat transfer are very large. So, we do not come across we do not realize the effectiveness or realize the presence of these effects in macro systems, but in micro systems, as the gradients keep on increasing at high value of the gradients, these effects start to play an increasingly important role. So, when we think about mass transfer, we not only should look at what is the concentration gradient and thereby use Fick's law, that is use the normal diffusion coefficient denoted by DAB, but we also have to see what is the temperature gradient in between the 2 points where such a mass transfer is taking place. So, both the value of DAT and the value of DAB needs to be taken into account, and the relative importance of concentration gradient dependent mass transport and temperature gradient needed temperature gradient controlled mass transport, both will have to be taken into account, and the relative magnitude of each of these will have to be considered and the right expression to be used for microsystems. The same applies for energy transport by temperature gradient as well as by other gradients. Now, when you look at the values of these diffusion coefficients, for example, DAT and DAB, you would know that you will never come across a situation in macrosystems where where you have enough temperature gradient present in the system such that these two processes become comparable. So, let us see what are the values are. For example, the Soret coefficient is of the order of 10 to the power minus 12 to 10 to the power minus 14 for liquids, and 10 to the power minus 8 to 10 to the power minus 10 for gases. So, this shows the values are quite small compared to the corresponding effect of macro scale, and you need not use them in macro systems. But in microsystems, due to the enhanced value of the gradients, the species transport or the heat transport by such processes become important. So, this again shows the interdependence of heat and mass transfer in microsystems because of the presence of temperature induced mass transfer and concentration induced heat transfer. So, the process becomes much more complicated when you go to microscale, and these additional effects which were not present in macro systems become progressively important. So, this is something which needs to be looked into, and one should be careful about using the species equation or the energy transport equation, and they may have to add or they may have to include additional terms to account for the enhanced heat or mass transfer in microscale devices. So, these are definitely advantages. The presence of these effects can be an advantage in terms of higher transport, but at the same time one has to be careful about modeling such a process by incorporating these effects on one hand, and the nature of the coefficients, the values of these transport coefficients, they will also be different because of the presence of high temperature or concentration gradients in microsystems. So, next we would see some of the examples of processes where such enhanced rates are possible, and the presence of these enhanced rates has led to interesting applications. For example, fast nucleation of nanoparticles in small devices, and fast mixing in microchannels can be used for the production of nanoparticles in flow of droplets, as well as rapid chemical reactions and precipitations in bulk flow. But the main problem of production of nanoparticles or any particles in flow, for example, in a microchannel, would be that once the particles are formed, the tendency of the particles would be to go towards the wall, stick to the walls, and just create a nucleation point for further accumulation of particles around that, and thereby form a bigger particle or a cluster of particles that will start to affect the flow, and they will increase the heat transfer. So, these kind of sticking of particles to the side walls would enhance the pressure drop necessary to make the liquid flow in such microchannels, and in extreme cases this may even clog the entire channel. So, precipitation of, or rather the formation of nanoparticles, though would be can be effected in a much more efficient way in micro devices, but the precipitation of such particles, accumulation, agglomeration and sticking of such particles or particle assembly to the side walls can be detrimental to the overall operation of such devices. And once clogged or once such particles form or deposit on the microchannel, for example, it would be very difficult to completely clean such a surface and to reuse it. So, this creates additional problem for repeated use of such devices for generation of subsequent generation of nanoparticles. So, these are the drawbacks of the devices that one has to be very careful about. The next example that we see is an interesting example. It is about distillation and rectification taking place on a single chip. So, here if you look that we have a silicon wafer where using anisotropic KOH treatment, which you are familiar with, that the KOH essentially etches silicon depending on the crystal plane it encounters. So, that is why it is called anisotropic etching. So, that means in one specific direction the etching will be a lot faster compared to the other direction. So, as a result of which you can get nice shapes, the most common one being a V groove. So, the etching rate in the direction, in the perpendicular direction is a lot faster than the etching rate at the sides. Whenever they come and meet the another crystal plane, the etching stops. As a result of which the etching is self stopping when the two crystal planes meet, and you get nice V shaped channels etched on silicon wafer. So, the anisotropic etching property of KOH, hot KOH has been used on silicon wafer to create a number of channels using certain mask which has been. So, it is a photolithographic technique. So, using such a technique, a device has been made where there are channels, and in one channel and through the channels there would be a heated water ethanol mixture, and the temperature from the heated side the mixture will evaporate and it is going to condense on the opposite side of the channel. So, the rectification takes place because of evaporation of ethanol from the ethanol water mixture, and then subsequent condensation of the higher concentration methanol at the top of the cold side of the channel. So, here you can see the advantages. Everything takes place in a very small device. So, the attainment of equilibrium, the one that happens on a distillation column using a bubble cap tray, here you have a very tiny channel through which a mixture of ethanol and water is flowing, and you are having evaporation, or you are having boiling, and the ethanol comes out, the vapor and the liquid are in such a close proximity that equilibrium is going to be reached very quickly, very effectively, and then you condense the vapor which has been formed on the other side of the channel, and thereby you can now create a condition in which you will have proper enrichment, that is, you are going to get the higher concentration of ethanol at one side and higher concentration of water on the other side. So, such distillation and rectification devices are becoming more common in practice, but there are certain problems which needs to be addressed to. As I mentioned, the large surface area, it's providing high values of transfer, and the exchange rates are also quite fast. The short distances ensures that thermodynamic equilibrium is reached very quickly, but the main problem is the amount of liquid it can handle, which is the low throughput, and how do you manage the different liquids and vapor which are flowing through maze of such channels on a tiny device. And you also have to ensure that you also have to think about that you cannot have an gravity like in normal distillation columns, where gravity makes the vapor flow up and the liquid is going to come down, and there is going to mixing between the two. As we know that in micro devices, the body force, the importance of body force is rather small, and therefore, we have to think of other ways for the liquid and the vapor to move. And at the same time, since it is going to be a pressure driven flow on such a small systems, then how do we ensure that there is no leakage between two adjacent channels? So, that is another technological or fabrication challenge that one has to think about in order to have such devices developed for various applications. So, low throughput complex fluid management systems, prevention of leakage, these and the additional forces necessary for the fluid to flow and come in contact with each other are the bottlenecks that are still there, that there has been increasing effort to overcome these difficulties so that this becomes more common. Okay. Now, one way to address such thing is can we do internal numbering up? So, internal numbering up can help to increase the low throughput, but the moment you do internal numbering, then the proper distribution, equal distribution of liquid into many channels is another fabrication issue, is another problem that has to be looked into. So, we also have to have suitable geometries embedded into the construction, embedded into the channels itself, such that the liquids and vapors are guided properly, so that the liquids will go in a specific direction and the vapors will go condense at another point, and the entire process keeps on moving. So, there are definitely problems which are there, which needs to be solved before this gets wider application. But similar efforts are also underway for adsorption, other processes, other mass transfer processes such as adsorption, desorption, extraction, free convection and so on, and we will see some applications of that. For example, if we think of free convection, now we all know what is free convection is that when there is a temperature gradient, temperature difference between one packet of fluid and an adjacent packet of fluid, then the density of the hotter fluid will become less and it is going to rise due to buoyancy and to be replaced by cooler fluid from the surrounding. So, if we have a hot surface and a fluid, let us say air in contact with it. So, air near the surface will automatically rise, hot air near the surface will automatically rise to be replaced by cold air from the surrounding. So, in the subsequent two slides, we would see whether the effect of free convection is relevant, is important in microscale devices. Now, we all know that in free convection, the two dimensionless numbers which are important are Grashof number, which the expression for which is shown over there, and the Grashof number is nothing but this buoyancy force, and we have this beta, which is the thermal expansion coefficient. So, it is the different expansion of the gases and the corresponding changes in density at a constant temperature, which is going to cause the fluid to rise, and Grashof number is a characteristic of the flow, which is nothing but the ratio of the volume force to the viscous force. Okay. So, this tells us about the dimensionless number, Grashof number, which governs such a process. So, now the gap, if the gap is too thin, now if we have, so if your Grashof number, which is the buoyancy force by viscous force, so if the gap between two plates is very thin, then any buoyancy driven flow created inside a micro channel will be dampened by viscous forces if the two layers, if the two sides, two surfaces are very close to each other. Whereas, if you think of this room, then if the wall is cold, then the air near the wall does not feel the presence of the wall at the other end of the room. Whereas, in a micro device, the two sides are so close to each other that even if the air is becoming lighter, it may not rise through the thin gap due to the presence of viscosity, due to the forces exerted by the viscosity of such gases. So, viscous forces are going to dampen the convection, and the heat then is transferred solely by conduction. So, if we have two plates and at different temperature with air in between, in normal condition the air should rise and there would be some sort of convection process which is going to extract heat from the hot and deliver it to the cold. But since the viscous forces predominate and the Grashof number is such that there is no rise of the fluid in between the two plates. So, we have a static layer of fluid in between two hot plates, and the only mode by which energy can get transferred from the hot plate to the cold plate would be by conduction only. So, another number which tells us whether the free convection flow is laminar or it's turbulent is the Rayleigh number, which is the product of Grashof into Prandtl number. Now, since the Grashof number is low, the Rayleigh number is going to be smaller than 3 into 10 to the power 8. So, this is obvious that in such a small device, due to the importance of viscous forces, the flow is going to be laminar. It is going to be entirely ruled by viscous forces, and in fact, the Rayleigh number is going to be about 200 or so, and if that is the case, then the heat transfer augmentation by natural convection is going to be smaller than 1% of the total heat transfer. So, this tells us that for most of the cases involving free convection in micro devices, the effect of the free convection or natural convection can safely be neglected. So, natural convection is negligible for micro process technology. Now, what are the other factors that one needs to look at while thinking about or making such devices? One is definitely going to be the thermal insulation length. We know that for example, in a micro heat pipe, one of the major problem is the presence of parasitic heat fluxes which are there in the system, because if you have a channel made, and let us say the channel is made of silicon. So, we not only have flow of liquid from the hot side to from the cold side to the hot side, and then the evaporation is going to take place, which is going to extract heat, and then that heat, the vapor is going to come back and condense at the hot end, thereby releasing the amount of energy. So, this kind of phase change mechanism is the cause of the high transfer rates of these devices. But you also have, but the channel is going to occupy a small fraction of the solid area, okay, solid mass. The rest of these are going to be just only silicon. So, there is a possibility that the heat, instead of going with the liquid through the channel, can also pass through the large areas available for silicon. So, I can have conduction through silicon from the hot side to the cold side, as a result of which these parasitic heat transfer can reduce the overall efficiency of heat transfer of micro devices. So, the thermal, how do we insulate a very small section from another section? If we cannot insulate it, then the high temperature gradient is going to cause enough heat transfer in between the two. For example, the distillation chip that we have seen in the previous figures, think about these are the three adjacent layers. So, I am going to have hot ethanol water mixture coming in, and then it flows like this. Now, unless we maintain the temperature gradient properly, then we are not going to have any rectification. But since these channels are very close to each other, then if I cannot if I cannot insulate these two properly, then everything is, there is going to be a temperature homogenization effect as a result of enhanced heat transfer, which is detrimental to the overall efficiency of any such device. So, how do we thermally insulate? It is extremely difficult. The advantage is that it has high surface area for transport processes. When we miniaturize anything, the area is decreased with the proportional to the square of the length, and this L square, the proportional dependence on L square, this is playing a major role for the enhanced transport fluxes in such devices. So, what are the challenges that we have? Obviously, low flow rates, low throughputs, and high pressure loss. So, this is in conflict with mass production of any material. So, since we cannot make a large quantities of something in such devices, so the material which is fit for production in such devices would be fine and specialty chemicals, okay, which are otherwise difficult to make, where there are other problems, where it is highly exothermic, where there are side reactions, undesirable side reactions which needs to be curtailed. So, these are the, and where the final product is very costly, and it has to, it can be prepared, it needs to be prepared in small quantities only. Okay. If such are the products, if such is the product, then microchannel or work in micro devices, production in micro devices would be beneficial, would be relevant. And the high surface to, and another thing that we have read is that the high surface to volume ratio may lead to amplified phenomena like material interaction or species adsorption, and this may have undesirable consequences as well. The fouling and clogging also decreases the flow rates. It may increase the pressure drop, and distribution of the flow can become hampered, and the reusability of the devices are also put to question. But the trend is now therefore to use disposable devices that can operate in a certain number of times, and then they can be substituted with new devices. So, this is another approach, though, as with increasing ease of production of these micro devices, since the fabrication techniques are becoming more simpler. So, mass production of these devices are becoming easier. Once we can produce such devices in a large quantities, then obviously the shift would be from reuse to disposing those devices after a few uses. So, that is the current trend, which where we are making disposable microfluidic devices for specific applications. And finally, the interplay of fluid mechanics, heat transfer, mass transfer, and chemical reactions in microchannels is still not understood to such an extent such that we can design, devise and fabricate a device for a specific application. So, it is an open area of research which needs lot of attention from all sides to understand and to utilize the plus points of such things. Now, we come to the part 2 of this course, where we are going to concentrate more on the fundamentals, the balances and the transport processes. The goal is that, starting with simple atomic encounters from statistical mechanics, some macroscopic balance equations and transport properties, how we can write fundamental equations that describes the transport processes in micro devices. So, we are mainly going to look at the mixing and separation unit operations, and the next table groups these operations according to their driving forces. I will skip this portion. Just let us just take one example. Now, if you think about mixing and aggregation, okay, and if you think on the molecular level, then diffusion is a root cause, okay, and there could be some thermal component to it as well. When you think about mechanical, then the mixing can be achieved by spraying, or there can be electrophoretic mixing as well. So, this table essentially lists the processes the unit operations, the molecular and thermal reasons, the mechanical forces that are necessary, and other electromagnetic forces. So, you can go through these to learn more about the importance of different forces in such operations. But we are going to concentrate on the balance and the transport equation. Now, we are very much familiar with this type of equations where a system change, a change in any property of the system. It could be the mass of the system, and the change in the mass of the system with time is a result of net flow, that is incoming flow, outgoing flow, plus if there is any generation inside the system itself. So, if we have a chemical reaction taking place inside such a system and a species A is being consumed, then the conservation equation simply tells us that the rate of change of species A inside the control volume would be equal to the net rate of heat addition, net rate of addition of species A through the boundaries. Now, through the boundaries the species can be added as a result of convection or as a result of diffusion. As a result of convective processes, that means with the flow some species A may come into the system, or there may be conductive fluxes exist across the boundaries as a result of concentration gradient. So, net addition of A to the control volume by convection and conduction plus generation or depletion of species A by reaction taking place inside the control volume. So, that is the general form of any conservation equation. So, we would also like to start with that conservation equation where the system change with time is a result of all these. Now, there are several ways by which you can generate a macroscopic balance equation. You can take a control volume and find out the ways by which something is being added to the control volume. It could be convection, it could be conduction, and the way it goes out of it, and there could be some amount of generation of energy, generation of a species in such a system. Or in the other words, you can look at a differential channel element and make heat balances such that you have, let us say, one hot fluid which is flowing. This is the solid boundary, and you have another fluid which is a cold fluid which is moving in the other direction, and then you have heat transfer across this from the hot to the cold. So, you can take a control volume, defined by certain distance, and therefore, find out what is the total heat that is being added to such a system. So, this should if we can think that it is just a 1D process, then it's simple, it's a 1D differential, we can take a 1D differential element and make such balances. So, whatever we have described so far, the general equation is the temporal variation, temporal and spatial derivative of a system within, and a differential element can be written in this following form, which is just the property, and the variation, temporal variation and the spatial variation of that property is going to be equal to the temporal variation of the quantity itself. So, if it is a steady state process, then this is going to be equal to 0, and this is simply in minus out plus or minus generation is going to be equal to 0. So, that is the standard form which we are mostly concerned with. So, in systems with high velocities, the convective transport is going to be dominant, and if it is a system with low velocity, but high gradient, then conductive and diffusive fluxes are going to govern. So, one has to think which one is going to be important. In many bulk flow cases, in many macro cases, for flow systems the convective transport will predominate, whereas in micro systems the likely chance is that the diffusive fluxes are going to predominate, and the effect of convective transport is rather small. But one has to look at these processes, each of these processes separately, to see what is going to be be the predominant case in this. So, if we have time dependent mass flow rates, then it is in minus out, and the momentum of the fluid can also be expressed as a result of the product of the mass and flow velocity, and we know that this has resulted If we think about the conservation of momentum, then that would give rise to equation of motion, and a special form of the equation of motion is Navier-Stokes equation. So, we would see what are the terms that would be important in Navier-Stokes equation, and flow in very long channels, how it can be modified. So, these are I will skip part of it. Now, if we think of non-viscous flow in an arbitrary channel, then the momentum change rate, time rate of change of momentum, is the momentum that is coming in, the momentum that goes out with the flow, the pressure, the surface forces which are acting in the form of pressure, the body force, and any additional force, any other force which is there in this. So, this is essentially the starting point of Navier-Stokes equation, and this results to additional forces in microfluidic applications, which could be due to different surface forces. So, similar to mass, the energy is also conserved, and the energy dissipation will take into account the energy conservation from one to another, and which is accompanied by natural losses. So, whenever energy gets converted to another form of energy, there will be some losses which cannot be recouped, and in fact, the conversion of energy from one form to another during such a process, the magnitude of that energy which dissipates is essentially tells us how efficient the process is. So, that is something one has to look at. So, these losses are characterized by entropy generation, and the more the entropy generation, the less efficient would the process be, and one has to devise or design the devices in such a way such that the entropy generation would be kept to a minimum. Now, this in the case of a channel with a constant cross section, the energy from the first law of thermodynamics, the energy is going to be sum of the internal energy, the kinetic energy, and the gravitational energy. So, this form of equation is quite well known to us, where this epsilon stands for the dissipation. So, this is the dissipation function, and this is essentially the temperature. This is essentially the temperature gradient induced conductive flow of heat into the control volume. So, if you use the caloric equations of state, this would look like this energy equation can be rewritten in the form that we are aware of. So, if it is so we have the left hand side, which is the convective flow of energy. The last term on the right hand side is the conductive transport of energy, and it is an isobaric process. If it is an isobaric process, the epsilon in this is the dissipation function, where any transport of energy, any flow is associated with entropy generation. So, this dissipation function is denoted by epsilon. So, here K is the thermal conductivity, and the solution of this equation is gives us the temperature distribution in any substrate. So, if it is an isobaric process with no dissipation, then these two terms will not be there, and what we will simply have would be rho Cp dt over time is going to be equal to divergence of K grad T. So, this is the form of the energy equation with which we are mostly familiar. If it is a system with generation of heat, then this Q dot would denote the amount of heat which is generated per unit volume of the system. So, this is the normal form of energy equation. Now, if the total amount of heat that is transferred is in a reaction system is given by this. So, if we divide the total amount of heat transferred divided by the temperature, we get the definition of entropy. So, in any such process, if we skip this part, the dissipation function epsilon is the friction loss per unit volume and time unit. So, this epsilon is in shorter form, this epsilon is connected with entropy generation in the process. So, entropy always increases by dissipation, and in any irreversible process such as pressure loss or concentration homogenization by mixing. So, if the value of this dissipation is large, if the value of the energy generation is large, that simply denotes that the system is not very efficient. So, the entropy production is a major indication of the efficiency of a process. So, the design should be such that the entropy generation can be kept to a minimum, and for an example, if you have a sudden expansion in the flow area, okay, and the liquid was flowing through a small conduit and suddenly it expands to a large area. So, in such cases, for example, in throttling, we need to minimize throttling in order to minimize entropy generation in a system. Similarly, if there is a sharp bend in the system, then the dissipation, the head loss would be much more and the entropy generation would be more, and the process becomes less efficient. So, any design has to be thought about, has to be analyzed to see how much of head loss, how much of energy generation that is taking place. So, sudden expansion, contraction, sudden change in the flow path are certain examples which need to be avoided in order to maximize the efficiency of the process. And various control strategies are applicable for energy saving and entropy minimization, and these are some of the examples that I have already mentioned. The additional ones are that for if we have a continuous flow system, the pressure losses should be kept to a minimum, and we need to minimize unnecessary throttling, as I have already explained. And if you are thinking about mass transfer operations, then high solution concentrations and high dilutions, these are to be kept to a minimum, as if you want to concentrate a solution to a very high value, or if you would like to dilute something, if you want to get a highly diluted solution, these are going to involve larger efforts, and any effort is going to give rise to entropy production, thereby reducing the efficiency of the process. So, in microsystems, these are going to be even more important, because as we know that in microsystem the viscous forces will predominate, and this energy dissipation, energy dissipation is a strong function of the viscous processes taking place at the interface. So, for systems in which the viscous forces predominate, the chances of viscous dissipation would be much more, even though the flow velocity is very small. So, so we are going to get more dissipation even for a slow moving fluid, if the slow movement of the fluid takes place in a microsystem. We all can visualize in a high speed flow in a macro device giving rise to entropy generation, and thereby reducing the efficiency of the process. More frictional head, more head would be lost due to friction. But in small systems, since it is governed by viscous forces, since the gradient is large, and very simply in the very simplified form, this dissipation function is proportional to the viscosity and is proportional to the gradient, velocity gradient square. So, since it is proportional to the velocity gradient square, and we know that in microfluidic systems the value of the velocity gradient is large. So, the head lost, the dissipation due to fluid friction even for slow flow can be large in microfluidic systems. So, viscous dissipation or any kind of dissipation needs to be carefully examined in microfluidic devices. So, all the equations that we have seen or we are going to see would be valid, many of them would be valid if continuum limit is maintained in a micro device, but the effect or the contribution of dissipation function corresponding rise in entropy and therefore, reduction in the efficiency of the process needs to be looked into very carefully. So, that is what I would like to conclude today, that we would for example, in any heat transfer device also, since it involves large gradients similar to large velocity gradients, the large temperature gradients will also give rise to higher entropy generation in microscale devices. So, these are the that is the peculiarity of the process and the device that we have to be careful about. Thank you.